get started. The next speaker is Vikram Sharma, my colleague at IMSC, and he is going to be talking about some general techniques for solving recurrence equations.
Thank you, Venkatesh. Can you hear me back there? Okay. Just keep me reminding if you can't hear me. So Professor Pandurangan had given us a very nice, subtle introduction to the various facets of divide and conquer algorithms. So what I will do in this talk is try to give some idea of the kind of tools and techniques that help us to solve recurrences. Okay. And most of the times I will be interested in some big O analysis. So let's see. You can say tools for solving divide and conquer recurrences. Okay. So as was mentioned, a general divide and conquer approach does the following. We have a problem of size n, and in the previous lecture we had seen that the problem was split into two parts of some smaller size. But in general what we do is we split it into, say, A parts, and say each of them is of size roughly n by b. So we have this problem of size n, we break it into A parts, each of size n by b, we recursively solve these A parts, and we combine the solutions. This is the marriage phase, and to get the complete solution for the problem. So let's say Tn is the overall complexity of solving the problem for size n. Then what we have is the recursion is to solve this problem of size n, I need to solve A problems of size n by b, plus I need to do this some work, let's say some work which is given by some function d of n, to combine the solutions to each of these small parts. Okay. So in general what we want to do is we want to solve recurrences of this form. Okay. We can generalize this further, but let's just keep it to this form where the problems are of the same size, the sub-problems are of the same size. Even further generalization could be where the problems, the sub-problems are of different sizes. Okay. But let's not worry about that. So our aim is to, say something of the form that T of n is order of something. This big O notation, is everyone familiar with the big O notation? So big O notation says, so if I say some function f of n is big O of some other function g of n, that means there exists some, let's say some number m large enough such that for all n beyond this number m, f of n is less than some constant times g of n. So if you draw this graph of these two functions, so this is, say, the origin, then there is some number m such that f of n is like this, and g of n is some constant times g of n is greater than f of n beyond this. Okay. So below this they may cross over. So I don't care about that, but I know that there exists a large enough number m so that for any value of n beyond this m, greater than this m, this constant times this function g of n dominates this function f evaluated at n. Okay, so what we want is to make a statement that T of n is order of some function, and we want to figure out what this function is. Okay, in the previous lecture we were doing exact analysis. We were not. We were very careful about the constant involved in this O. Okay, we went from this 2n to 5n by 3 and then 3n by 2. But here we won't worry about the constant. We want to get a rough idea of how this function behaves. Okay, what is the complexity of the problem, asymptotically speaking, for large enough sizes of the problem. Okay. So, well, one way to solve this one is, if you have taken a standard course in algorithms, is to use Master's theorem or Master theorem, right? But Master theorem, first of all, I can't remember Master theorem. So if you have a poor memory like me, then you are into trouble. There are these three cases, which one is what, when is it true? So I don't want to rely on Master theorem for solving this. In fact, most of the times Master theorem may not be able to solve this. So what I want to do is I want to start solving such problems, solving such recurrences from fundamentals. Okay. And for that, what we'll start with is fundamental recurrence, which we had seen in the last talk as well, which is of the form, the function s of n is Sn minus 1 plus d of n. To solve this problem of size n, I need to solve a problem of size n minus 1, plus I need to do some extra work. Okay. So we had seen this in the last lecture, in the previous lecture. And why is this the fundamental recurrence? Because, okay, let's give an example first. So one problem which I can solve in this, which has this recurrent structure, is if I want to add n numbers, right? If I want to add n numbers, 1 to n, let's say, or a1 to an, I just pick one number, I add the remaining n minus 1 numbers, and then I add this one number to the sum obtained by adding a1 to n minus 1. Okay. So if I have n numbers, say a1 to an, then my recurrence would be, I'll add these first n minus 1 numbers, and then I'll get this sum Sn minus 1, and then I'll add a into this sum. Okay, so the recurrence in this case satisfies Sn is the time to add, complexity to add n numbers is the complexity to add n minus 1 numbers plus constant operation to add an to this. Okay. So if we have this, if we have a recurrence in this form, the solution is very easy to see, and the trick is the same. So what is the trick? So I write Sn minus 1 is Sn minus 2 plus Dn minus 1, and similarly Sn minus 2 is Sn minus 3 plus Dn minus 2. So on, I'll get S1 is S0 plus D1, right? So this is, the recurrence satisfies this. So now if I add all these equations, what I get is when I add these on the left hand side and when I add these on the right hand side, I see that these cancel out, right? This telescoping effect that was mentioned in the last lecture. So what we get is, so let's say S2 would be S1 plus D2. So S1 cancel out. So what I get is Sn is the last term S0 plus the summation D1 plus D2 plus 1 Dn. So if I can sum these terms easily, if my function d has a very nice form, let's say dn is just n. Okay, if dn is just n, then I can write this summation in a very nice form. I'll get, in that case, I'll get Sn is just S0 plus the sum 1 plus 2 plus so, which is just S0 plus the sum of the first n numbers this quantity. Okay, so S0 is the base case here. So S0 is the base case. Let's say S0 was 0. It can be 1, it will be some constant. So what we get is that Sn can be simply written as the summation from 1 to n of this driving function di. Okay. So the nice aspect of this fundamental recurrence is that it has this closed form in this summation term. Okay. And if your function d is nice enough, then you can plug in that function d, for instance, when in that case when dn is n, and you can get a nice form for your recurrence, a nice closed form or some upper bound on your recurrence. Okay. So what we want to do is, in the long run, we want to reduce a recurrence of this form, a general divide and conquer recurrence, to a recurrence of this form, fundamental recurrence. Okay. So we'll reduce this recurrence to this fundamental recurrence. The fundamental recurrence has a nice form solution, and then we'll pull back and see what this recurrence, the original recurrence T has, the structure of the original recurrence, okay, the solution of the original recurrence. So we'll do it in 2 stages. So let's start with a slightly more involved recurrence. Let's say of the form So it's involved then the fundamental recurrence, because I have introduced this some constant a. Okay. So let's say a is some positive constant. So do you know any recurrence of this form? Of this structure? You have to solve a problem of size n, I have to solve some a problems of size n minus 1, and then I have to do some extra work. Insertions or what is the recurrence? A not 1, yeah. If that is the case, then okay. One example is this Tower of Hanoi. Right. So Tower of Hanoi is to solve the Tower of Hanoi, solve the problem of size n for n disks. I have to solve 2 problems for n minus 1 disks, and then I have to do this extra work of switching the largest disk. So Tower of Hanoi has that form. Okay. So it is a divide and conquer approach, but we have this factor of 2 sitting. So I want to reduce. So my first step is to reduce a recurrence of this form to a recurrence of this form, to a fundamental recurrence. Okay. So how will I do that? So the trick to do that is called a range transformation. We'll see why it is called a range transformation. So I'll define a new recurrence from this recurrence. Okay. So I'll define my S of n as R of n divided by a raised to n. Okay, I divide Rn by a raised to n. And now my claim is this function satisfies fundamental recurrence. Okay. So why? So what I have done is I have divided both sides by a raised to n, a raised to n, a raised to n, and what I get, this is Sn, this is Rn minus 1 upon a raised to n minus 1, and that is just the driving function. But what is this term? That is just Sn minus 1 by definition. Okay. So what we have done is we have reduced this recurrence, this recurrence, it's of type 2, to a recurrence in the fundamental form. Okay, and now what we had seen here, I can solve that fundamental recurrence directly. So I can write that Sn is just the sum from I from 1 to n of di upon a raised to I here, plugging in this thing. Okay. And now what do I, so now but I want the solution for Rn, so I know that Sn is I from 1 to n di a raised to I. So from the definition I get that Rn is a raised to n times S of n, which is just the sum di a raised to n minus I. Okay. So again we have expressed our the solution for a recurrence in terms of the sum, and if we can compute the summation easily, then we have a closed form for our recurrence. So in particular, when we have let's say in this recurrence, what do we have? Our d function is just a constant. dn is just 1 always. So what do I get? For our example, we get Rn is summation I from 1 to n, a is 2, so 2 raised to n minus I, and di is just 1 always. So the solution for this recurrence is the sum. Okay. And this, what is the value of the sum? This is the geometric summation. So I can rewrite it again as I from 0 to n minus 1, 2 raised to I. So this is 2 raised to n minus 1. Okay. So the idea is always to, given any recurrence, we want to reduce it to a fundamental recurrence. Fundamental recurrence, we know the solution. Apply the solution back here in this for the recurrence that we have, and you will get a nice closed form. Okay. So why do we call this a range transformation? We call this as a range transformation because the function s and this function r of n, so these are functions from the natural numbers to say the natural numbers. Okay. They take in some natural numbers 0, 1, 2, so on, and they output some natural number. So that is, both s and r are functions from natural numbers to natural numbers. And by definition, what we have done is, by definition, we have not changed the domain of these two functions. The domain is still the natural numbers, but what we have done is the range of s is changed, is a scaling of the range of the function r. Okay, we have changed the range of the function r. So we have transformed the range of this function. So r is a function, this is a domain, this is a range. So you have changed the range of r to get this new function s. So you have transformed the range of our recurrence to get a recurrence in the fundamental form. So what have we? So what can we answer now? We can answer queries of, we can solve recurrences of this form so far. Now what we want to solve is recurrences of this form, and then we have to somehow combine the two forms to get a recurrence solution for this recurrence. So now let's say our recurrence is, so u of n is u of n by b plus the driving function d of n. So we do any problem that fits in that pattern. To solve a problem of size n, I solve one problem of size n by b, and then I combine the solution in time d of n. Binary search, right? So for binary search, to search a number in an array of sorted array of size n, you have to search in a sorted array of size n by 2 plus one comparison to the midpoint.
Last lecture I figured that the floor and the ceiling usually having the problem if you are doing the divide and conquer. You are splitting the problem into these steps. So how do you do the ceiling and floor?
So ceiling and floor, I'll replace it with an upper bound. I'll just say, so most of the times when we do this solution, the function is monotone. So using that, you can say the ceiling or the floor is just upper bounded by 2 times n by 2. Or more generally, it's easier to think of n as not an integer but as a real number. Then you don't worry about the ceiling and the floor. Then you can treat your problem, you can do induction over the reals. There is an approach to solve these recurrences where you have ceilings and floors by doing induction over the reals. Okay, so yeah, let's come back to this problem. So this recurrence. So now I want to do the same thing as we have done here. I want to reduce this recurrence of u to this fundamental recurrence. And so what do I do now? So what we'll do is we'll define, say, okay. So let's say n is some power of b raised to k. Okay. And then we'll define s of k to be u of n, which is so define s of k. So k is roughly the log of n base b. Okay. So we define s of k as the function s of k as the function u evaluated at b raised to k. So here again there is this issue which we had in the last lecture. You don't want to do that always if you want to be very careful with your analysis. But for an big O order analysis, you can work with that. Okay, if you want just an asymptotic bound on your complexity, you can look at the value of the functions at these powers of b. And then if you get some bound, you can go back and do a proof by induction to show that the bound is valid for all n. But let's say, so this is our definition of S now, and our claim is with that definition S has this fundamental recurrence. Okay, S satisfies the fundamental recurrence. So why is that? So what we have done is u of n is just S of k, u of n by b is b raised to k by b plus d of b raised to k. And what is this quantity? That is u of b raised to k minus 1 plus the driving function, and by definition u of b raised to k minus 1 is just s of k minus 1. So we have reduced our original recurrence from this structure to the fundamental recurrence. Okay. And now we can again plug back this solution from here. What we'll get is Sk is the summation I from 1 to k d of b raised to I. So it's kind of a geometric summation. Okay. Is that visible? And so what we have done is here we have modified the domain of our function. Okay, we have played around with the domain of our function. So our function was, our recurrence was defined on n, and from n we changed to k. Okay. So we have transformed the, so instead of looking at the value of n, we are looking at the value of log of n rather, and evaluating this function s at the log of n with base b. So and k is by definition log of n base b. So this approach is called the domain transformation. So this was the range transformation. Here the domain, the variable remains the same, n. Here the variable changes from n to k. Okay. And the claim is using these two transformations, either transforming the range or transforming the domain, you can reduce this general recurrence to the fundamental recurrence. Okay. And once we do that, once we reduce the general recurrence to this fundamental recurrence, we have this nice solution. We can go back and get a solution for the original recurrence. Okay. So we don't. So the nice thing is we don't have to remember any of these master theorem cases or anything. You just have to remember that how can I reduce this recurrence to a fundamental recurrence, and once we can do that, we have a solution. Okay, in fact, even to prove master theorem, you can use this approach. So now let's see how to combine this range transformation and this domain transformation to reduce that general recurrence to this fundamental recurrence. So this recurrence combines both the elements from this recurrence of type 1, let's say, and this recurrence of type 2. So it has an A like type 1 recurrence, and it has this B like type 2 recurrence. So I have two options now. I can apply either the range transformation or the domain transformation. A raised to n. Okay. So if I plug in this definition, n is a t n by b plus a raised to n plus dn divided by a raised to n. And this a cancels out, I lose one a, so I get Tn by b, a of n minus 1 plus dn divided by a raised to n. Okay. So I have applied the range transformation here, and now I have to apply the domain transformation to get rid of this n by b. Okay, so if I do that, if I plug in, okay. Let's plug in n is equal to b raised to k. Then what? So uk is t of bk minus 1. So what I'm doing, I'm defining uk to be t of rather r of b raised to k. Okay. So this was the range transformation n by n. Now I'm doing the domain transformation. I'm defining uk to be r of b raised to k. Okay. So if I do that, what do I get? I'll get uk is t of bk minus 1 upon a of n minus 1. This, okay. So this is, I wanted this to be in the fundamental form, fundamental recurrence in this form, but it's not. Okay, because this is not uk minus 1. I want this to be uk minus 1. this is not going to work. Applying a range transformation first and then applying a domain transformation does not give me a nice fundamental recurrence. Okay, so let's switch gears and go the other way around. Let's apply the domain transformation. So d of b raised to k, or I'm defining n as some power of b, is a of t of b raised to k minus 1 plus d of b raised to k. Okay. Now this is, by definition, t of b raised to k minus k, r of k minus 1. So what we have is, we have got this recurrence which is now of that form, of type 1 form. Okay. So applying the domain transformation first gives me a recurrence of type 1 form, and now I can reduce a type 1 form to the fundamental form. How I define s of k as r of k divided by a raised to k, and again that I'll get s of k is s of k minus 1 plus this driving function evaluated b raised to k divided by a raised to k. In this form, in this fundamental form. So now that is in this fundamental form, and we know that we can solve it. So what is the solution for the fundamental? S of k is summation I from 1 to k, d of driving function is b raised to k, b raised to I divided by a raised to I. So that is the solution for the fundamental recurrence. Now I want the solution for this recurrence r of k. So I multiply both sides by a raised to k, so I get r of k is this sum. Okay. So I got the solution for, plug in n is equal to b raised to k. Or yeah, I plug in b is this kth root of n. So I is going from 1 to k is log of n base b. Driving function is b raised to I, which is n of I by k, and a raised to k minus I. Let's say I pull out this a raised to I, and what is a raised to k is just a raised to log of n base b. Okay, and so I can rewrite this as this out of the summation. I'll get a raised to log of n base b, and this nice sum, this driving function at I by k of 1 a raised to I. And what is this thing? We can reorder this to get b, and this sum remains the same. Okay. Right, we can switch a and n, so n comes down, a goes up. So what we have is that this recurrence, the solution to this recurrence, so if you recall the master theorem, this function is crucial there. This is the watershed function. So that comes out of picture. Okay. So what have we done? We have reduced the domain transformation and then a range transformation, and then reduce it to this fundamental recurrence. Got the solution for this fundamental recurrence and plugged it back to get this final solution for a general divide and conquer algorithm. Okay. So as such, it is not very useful. If you see this formula, it's perhaps it's a bit hard to remember, but the whole point is we don't want to remember the formula. We just have to remember that we have to reduce this recurrence to this recurrence. That's it. Okay. And then do the necessary manipulations to get back the closed form. So let's apply that formula to some recurrences, some interesting recurrences. So one interesting recurrence is, you've seen it in many contexts, is the recurrence, let's see. Okay. So do you know of an algorithm which has this recurrence? Merge sort. Right? So I'll describe a different algorithm, a more geometric algorithm, not for merge sort, of course, a different geometric algorithm for computing a convexel of a set of points in the plane, a divide and conquer algorithm which has this recurrence. Okay. So let's see. So what is a convexel of a set of points? So suppose I have So the convexel of these points, let's say these points are pegs, okay, there are these pegs put at these points here. So the convexel is roughly, if you take a big enough elastic band, you put it around this, all these points, and then you leave this band, it will close on these points, right? Take a big elastic rubber band and let's say so that it closes all these points, and then I leave this rubber band. Okay, so when I leave that rubber band, it will hit these points which are at the extreme, right? So when I leave this rubber band, I'll hit the rubber band, will peg on all these points, and the structure what I get is called the convexel of the set of points. Okay. So convexel basically, you are looking at all the points which form this, given a set of points, all the points which are in some sense the extremal points in this set. Okay. So these inner points do not form part of the convexel. The convexel is defined as this structure, this convex polygon. So what we want to do is, we are given this bunch of points in the plane and we want to find this convexel of the points. Okay. So mathematically speaking, it's the smallest convex set which contains all these points. Okay. So what we want is a divide and conquer algorithm, and our claim is that algorithm will have this recurrent structure. Okay. To find the convexel of n points, we'll find two convexels on points n by 2 points, and then we'll combine those two convexels to get a complete convexel for the n points. Okay. So given this bunch of points, I want to break it into two sets of roughly equal size. I want to find the convexel for those two sets and then combine the convexels to get the complete convexel. Okay. So is the definition of convexel clear? So what do we do? How do we split these roughly 2 halves. Okay. So what we do is, so let's take the x and the y axis. So the first step that we do is we project all these points on the x axis, or in other words, we just look at the x coordinates of these points. Okay. So let's say we project all these points to the x axis. So I'll get this bunch of points. I'll get this bunch of points on the x axis, the x coordinates of all the points. Okay. And now what I want to do is I want to just consider these x coordinates and say consider a line such that half of the x coordinates are to the left of that point, half of the x coordinates are to the right of that point. Okay. So what point should I choose? I want to find a point x somewhere here, so that half of the x coordinates are to the left, half of the x coordinates are to the right, roughly. So what point x has this property? Median, right? So let's say I find the median of these points, and the next talk we'll see how to find the median. Okay. So suppose I find the median of these points in order n time, linear time. Okay. So if I can find the median of these x coordinates in order n time, what I have done is I have drawn this line which at this median, and I've considered all points roughly n by 2 to the left of this line, and all the points n by 2 points to the right of this line. Okay, that is my partitioning, that is my divide step in this divide and conquer. So I have n by 2 points here, I have n by 2 points here, and what we do is we recurse on these n by 2 points. So what we get is, when we recurse, what we compute is the convexel of this convexel, and we compute this one point, this convexel. Okay, so these are my n by 2 points, n by 2 points, and we are recursively computing the convexel on these two parts. So I get a convexel like this, and I get a convexel like that. Okay, so that is this step in the recursion, and what we want to do is now is to compute the convexel, this complete convexel. Okay, given these two small convexels, I want to find the convexel of all these points. So how to do that? So my claim is even that can be done in, say, order n time. I'll use a different color. So what do we want to find? We want to find these two lines, right? We want to find this line from this topmost point to this topmost point, and from this bottommost point to that bottommost point. Okay, once we have found those two lines, we just combine them, and we know that if we drop these two inner these two segments, what we have is the complete convexel. So the approach to do that is you pick, let's say, the rightmost point of this convexel and the leftmost point of this convexel. Okay, so you look at the point closest to the median for this convexel and this convexel. Okay, and you connect them by some line, if you can connect them. So that is roughly the bridge connecting these two convexels. Now what we want to do is we want to make this bridge as horizontal as possible. Okay, so as horizontal as possible means, so if I'm at this bottommost point, what I want to find is this segment. So I start seeing if there is a point smaller than this, so that my bridge starts to become horizontal. Okay, so I'll take this bridge, and I know that this point is smaller than this, so if I draw the bridge like this, my bridge has become more horizontal. Okay, so we draw this bridge. Now again, this point is smaller than this, so I can make my bridge even horizontal by taking this point. Okay, for if I go further my bridge is only going to increase. It's going to become more inclined. So I don't go any further. This is the bottommost bridge. Okay. Similarly, I can do now the other way around. I have to increase the bridge. I have to go to the topmost bridge. Here I reach the bottommost bridge. To go to the topmost bridge, I'll start going like that. I'll pick the point higher than this, so that my bridge becomes more horizontal, and then like that.
You don't necessarily want to make the bridge as high.
Yeah, that's true. So you can have that structure. So still, this is the best that you can come to. Anything below that is going to make it more inclined. Anything beyond that is going to make it more inclined. So bridge is very informal. What I want to find is a tangent connecting these two convex cells. Okay. Yeah.
Suppose the point, there's a common point between both the segments that lies on the median, and that would be the.
No. Then I'm not splitting it into two parts.
No, suppose it's like something like this. So this point lies on the median.
Yeah, but
How
I'll.
will you determine the leftmost and rightmost points?
No, I'll put that point into one set and not in the other set. So these 2 point sets will never overlap. Okay. So you never have a point common to both the sets. Okay. So what I want to say is there is a nice linear algorithm to find the upper tangent and the lower tangent. Okay. If you play around that idea, you will figure out that there is a nice linear algorithm to find the upper tangent and the lower tangent. So what we have is this nice recurrence. To compute the convex cell of n points, I can compute two convex cells on points of size n by 2 roughly, and then connect them in linear time, assuming I can find the median in linear time. Okay. So that mystery will be solved in the next talk. So we have this recurrence for finding the convex cell, a divide and conquer algorithm for finding convex cell of n points. Okay. And if I use that approach, this domain and range transformation, then we can show that this is or even if you don't, you know that this is the same for merge sort, so it's n log n, right? So okay, so this is let's see, I have only, do I have time or okay, I'll look for I'll overshoot for 15 minutes, 10 minutes maybe. Yeah. Okay. So let's see another interesting recurrence, which is this recursion have you seen this recursion? Yeah, you have definitely seen it. Yeah, so this is a recursion for multiplying two numbers of bit length n. Okay. So A and B are binary numbers of bit length n. Then we know that algorithm for multiplying these two numbers, what is the complexity for multiplying two n-bit numbers? It's roughly order of n square, right? And the claim is this algorithm of Karatsuba again gives us a better running time. It gives us a better running time than quadratic, okay, better than n square. So what is the idea there? So the idea is roughly from this recursion I have to do multiplication, 3 multiplications of size n by 2 on numbers of bit length n by 2, and then some linear operations. Okay. The divide and conquer is that I break A into 2 parts, say A0 and A1. So A0 is the first n by 2, the significant n by 2 bits, the next n by 2 bits. Okay. So similarly, we do write B as B0, the first n by 2 bits of B and the remaining n by 2 bits of B. So if I take the product AB, what do I get? I get A0 B0 shifted by 2 raised to n plus A0 B1 plus B0 A1 shifted by 2 raised to n by 2, and then the product A1 B1. Right? So we get the product of these two numbers as in this form. Okay. And all these 4 numbers are of bit length n by 2. Okay. So if I do in this form, what do I get? I am doing one multiplication of 2 numbers. So this is a multiplication of numbers of bit length n by 2. This is another multiplication, another multiplication, another multiplication. So I have done 4 multiplications. If I do this approach, the recurrence I get is I have done 4 multiplications, 1, 2, 3, 4 of numbers of length n by 2 plus so here the cost of adding these two numbers of bit length n is roughly linear, order of n, okay, plus n. Okay. So if I do this form, the straightforward form, this recurrence, is this better than this? If you have a good memory, master theorem, this is not better. This is roughly, this is again quadratic. Okay. So to improve upon that, the crucial observation is you do this multiplication, you do this multiplication, but to compute this sum, what we can do is take A0 plus A1, this number, take B0 plus B1. Again, these are numbers of bit length n by 2 roughly. Take this product and subtract the leading term A0 B0 and A1 B1. This sum can be expressed as in this form. Okay. And what is the advantage of doing that? The advantage is I do one multiplication to compute this number, I do one multiplication to compute this number, I do one multiplication to compute this number, and I do 2 subtractions. Okay. So then what I get is I do 3 multiplications of number of size n by 2 and do some constant addition and subtraction. And if I solve that, okay, let's do that. So let's solve this using our domain and range transformation approach. Okay. So what do? I have to first do a domain transformation, right? So let's define R of k as t of 2 raised to k, or n is defined as n is some power of 2. So if I plug in that, I get R of k is 3 times R of k minus 1 plus 2 raised to k. Okay, so this is doing the domain transformation, and now I do the range transformation. I'll get I define S of k to be R of k divided by 3 raised to k. So then doing this is domain transformation, this is range transformation, and doing the range transformation, I get this is S of k minus 1 plus 2 by 3 raised to k. Okay. So we have reduced this recurrence into this fundamental recurrence. Now I can solve this fundamental recurrence. I know that this is just the sum of I from say 0 to k 2 by 3 raised to I. Okay. So that is my solution for S of k. To get the solution for R of k, I have to multiply by 3 raised to k. Okay. And to get the solution back for t, I have to substitute k is log of n, and so I get t of n is 3 raised to log of n summation I from 0 to log of n 2 by 3 raised to I. Okay. So this is that form, equivalent of this form. Okay. And now what is this term? So again I can switch 3 and n by some simple properties of the logarithm function, and this is a geometric summation, right? What is this sum? This is 1 plus 2 by 3 plus 2 by 3 whole square plus so on, right? But it terminates here, but since it is a geometric summation, I can take it to infinity, because 2 by 3 is less than 1. I can say that this is less than n raised to log of 3 summation I from 0 to infinity 2 by 3 raised to 1. Okay, I am just overestimating. It's a geometric sum, doesn't do much harm. And what is this geometric sum? This is 1 upon 1 minus 2 by 3, so that is just 3. Okay, so t of n is, the solution for this is t of n is, okay, or you can say it more precisely, it's less than that. So this is better than quadratic. Log of 3 is less than 2. Okay, so Karatsuba's algorithm is, so this is strictly less than, or this is say small of n square. Okay. So you can say, if you know master theorem, you can say that, well, you can directly go from this to this, right? If you know master theorem, you can say this is n. Okay, what does the master theorem say? Let's try to recall the master theorem. So for this recurrence, master theorem defines this watershed constant alpha as this log of a base b, and this watershed function n of alpha, and there are 3. First is if this driving function is say smaller than this watershed function n raised to alpha for some epsilon greater than 0. If that is the case, then what do we know? Then we know that this is going to dominate the sum. So then we know that Tn is it correct? Okay. This is a master theorem. So the first case is the driving function is order of polynomially smaller than this watershed function, then we get that T is order of n raised to alpha, which is the case here. The driving function is n and the watershed function is n raised to log 3. So n raised to log 3 is greater than n, polynomially greater than n. So we get that T of n is dominated by the watershed function. Okay. Case 2 is when both are roughly of the same order, the driving function and the watershed function. In that case, Tn is theta of n raised to alpha log n, and case 3 is when the driving function is much larger than the watershed function, polynomially larger. In that case, T of n is dominated by the driving function. Okay. So you could say, okay, if you know the master theorem, then for all the examples that we have seen so far, I don't need to do any domain or range transformation. Right? So what is the advantage of doing this approach? Okay. The advantage is, what if I have a recurrence of this form? Can I apply master theorem? Can I apply master theorem if my recurrence is of that form? I can't. Why? Because the driving function is n log n. The watershed function is, say, Wn is n raised to log 3. And the problem is n log n is not polynomially smaller than, it does not satisfy this inequality. That it's polynomially smaller than n log 3. Okay. So the master theorem breaks down when the relation between your driving function and your watershed function is logarithmic rather than polynomial. Okay. So is it clear that master theorem fails when the driving function is logarithmically related to the watershed function? But in this case, even when I have this situation, I can still do the domain and range transformation. Okay. So let's see. I'll just stop after this. So what will I do? I'll substitute the domain transformation. First, I'll say R of k is defined as, again, T of 2 raised to k, where n is some power of 2. So then my recurrence is R of k is 3 times R of k minus 1 plus 2 raised to k times k. Okay. Now I do the range transformation. Range transformation, I define S of k to be R of k divided by 3 raised to k, and if I do that, I get S of k is S of k minus 1 plus k times 2 by 3 raised to k. Okay, so we have reduced this recurrence to a fundamental recurrence, and we know the solution is 0 to k I times this summation, and going back I get R of k is again 3 raised to k times this, and T of n is 3 raised to log n summation I from 0 to log n I times So we can still do, even when master theorem is failing, we can still do the domain and range transformation, reduce our recurrence to a fundamental recurrence, and we get that T of n is this sum. Okay, how do we bound this sum? So to bound this, earlier we had just this geometric sum, now we have this I. So what we use, what property we use is that the geometric sum has this form: 1 plus x square plus x cube plus so on, x raised to I plus so on. To get that sum, to get this I should differentiate this this equality. So I'll get 1 upon 1 minus x whole square is 1 plus 2x plus 3x square plus so on, I x raised to I minus 1. And I have to multiply, since this is I x raised to I have to multiply this by x to get that. So I multiply throughout by x. So this sum is, if I plug in this equality, what do I get? This sum is, I have to plug x is equal to 2 by 3. So 2 by 3 and 1 by 3 is 9. What is it? 2 by 3? 1 by 3, 9. 6? 6, yeah. So 6 times. Okay. So we can still solve. We can still estimate our recurrence using the domain and range transformation. Okay. So to summarize, I'll stop with that. So to summarize, given any recurrence of this form, we should always try to reduce it to a recurrence in the fundamental form. This form, and once we have the recurrence in the fundamental form, we can do the summation. Usually it will be a sum of this form. You use some basic tricks from algebra and you reduce your summation to a nice form. Okay. So that way you don't have to remember any of this. You don't have to remember any of this, and it works even when master theorem fails. Okay. So this approach is more general than the master theorem. In fact, if you want to prove master theorem, you can follow this approach. The proof is essentially this. Okay. So in each of these three cases, you have to say that the sum that we get here, what is this sum bounded by when d of n is smaller, when d of n is the same as n of alpha, n raised to alpha, and when d of n is greater than n raised to alpha. In each of these three cases, the sum has a nice structure. You can simplify that, and what you get is these three claims. Okay. Yeah. Any questions? Thank you.